Hi everyone, I'm Andrea.
I'm Giorgio.
And I'm Francesco. We are the team leaders of the Sapienza Technology Team from Sapienza University of Rome. Since 2016, our aim was to bridge the gap between academic theory and space exploration, and we are here to present our latest product, CC8. To manage this complexity, we built a multidisciplinary team of 50 students from STEM, economics, and social sciences, organized in a highly specialized structure.
Our team is divided into 6 departments that work in total synergy. They are structure and navigation, responsible for the rover's chassis, mobility systems, and autonomous navigation. Instrument and manipulation, they handle the robotic arm, the drill, and every tool CC8 uses to interact with the environment. Then there's cameras and communication, managing every signal from high-def camera feeds to long-range links and the ground station. Science and mission operations, the brain behind mission strategy, test scenarios, and deep sample analysis. The drone department, designing and building our autonomous flight unit entirely from scratch, hardware and software. Management, the crew handling logistics, partnerships and communication. This year they also help us, the team leaders, in coordinating the project.
The European Rover Challenge has been our annual reckoning since 2022. We don't just show up to compete, we show up to find out exactly how far our engineering, our teamwork, and CC8 can go. Every edition leaves us with new skills, new scars, and a clearer picture of what it actually takes to build systems that perform when it matters.
The rover mobility system is built around a central chassis, a welded frame that houses the electronics and provides mounting interfaces for the robotic arm, the drilling units, and the antenna. The two rocker bogies assemblies are connected through a differential bar, ensuring stability and adaptability over uneven terrain. All wheels are driven, with the outer one providing steering capability. The wheels themselves feature a vertically layered structure with varying material stiffness to adapt to different terrain types. This year, the structure has mainly undergone maintenance operation, with changes focused on refining the pre-existing elements. Let's see it in action. The rover moves forward, then backwards. It turns right, then left. It handles a slope, up, and then downhill. And finally, emergency stop.
Inside the central module lies the rover's electronics core, which allows the software to run all tasks in a safe and reliable manner. In particular, we have the navigation electronics consisting of a central navigation master PCB and 5 slave PCB plus drivers, and last but not least, the onboard computer, the NVIDIA Jetson.
Our navigation stack is built entirely in ROS loop. For situational awareness, an Insta360 camera mounted on top of the rover provides a complete 360-degree view of the surrounding. The custom controller handles low-level motion, sending velocity commands to the steering and wheels, while receiving real-time feedback from encoders. The rover can also navigate autonomously.
Our autonomous navigation system uses a localization and mapping pipeline based on visual odometry from a stereo camera fused with IMU data.
This allows the rover to navigate uneven terrain and reach target waypoints without manual intervention.
Additionally, we've developed a full simulation environment using Gazebo, allowing us to validate navigation algorithms even when the rover is unavailable due to electronic or mechanical maintenance.
The camera and communication department ensures a safe and stable communication system with reliable video streams. Camera setups are specifically designed for each task, avoiding bottlenecks and trying to acquire as much information as possible. The CCH communication system operates on a 5 GHz low-band transmission backed by a secondary LoRa link for teleoperation in case of Wi-Fi failure.
Now it's drone time. This is our drone.
Thanks to last year's experience, we realized that components were not good enough for the mission, so we started over. We replaced the old flight controller with a PixOx 6C. Redundant sensor, PX4 firmware, and for localization we dropped GPS global position in favor of local position estimation using visual inertial odometry through an Intel RealSense stereo camera. The brain of the system is a Raspberry Pi 5 running all the high-level logic developed in MATLAB Simulink. The core is a finite state machine state flow. Mission state transitions are no longer time-based but driven by the actual state of the drone. Communication with the flight controller happens via ROS2 and the UXRCE DDS middleware.
But first thing first, the drone needs to fly.
Take off. Up. Down. Forward, right, left, backward, and landing. To house all this hardware, we are building a custom frame. Dead-cut dihedral geometry, designed to allow landing on a platform mounted on the rover we are developing in parallel. On the safety side, the system integrates multiple layers of protection. The auto-land system activates autonomously in case of RC signal loss. As you can see, we turn off the radio controller and the drone lands on its own, with no pilot input required. And that's it for the drone.
Now, it's scientific instruments time. Let me introduce you to our tools.
But first, CCA has something for you.
The robotic arm is capable of Cartesian trajectory planning using the robotics toolbox and autonomous implementation. The end effector integrates pressure sensors and its phalanges are designed for multiple task configurations.
In probing task configuration, the end effector grabs probes and deposits them in the container. For rock sampling, the gripper design allows the phalanges to adapt to the sample geometry. Pressure sensor data gives us real-time feedback on grip force. In the Astrobio task configuration, the phalanges were adapted to aspirate liquid samples through a syringe, next to the pH sensor. And now it's time to dig. This is our deep drilling system, and this is our surface sampler.
The drill is managed by a primary PCB for main control and a secondary one for individual motor management. We are integrating torque control via additional sensors to improve performances. The system drives 3 motors and reads from load cell and distance sensors.
The scoop module can gather soil samples through a synergistic motion with the entire rover. The tool is equipped with a steering mechanism and weight sensors to avoid further manipulation.
Mars is waiting. See you there.